When designing power diodes, there are various trade-offs. One is the trade-off between the blocking voltage or breakdown voltage of the diode versus the forward voltage drop versus the switching speed. And this is a trade-off that is inherent in any of our powered semiconductor devices. But it's interesting to see how it works in the PN junction type diode. In any semiconductor device, the breakdown voltage is related to the doping concentration of the silicon material. Basically, silicon with heavy doping has a low resistance, but it also breaks down at a lower electric field strength than if there was a light doping. This is a fundamental characteristic of avalanche breakdown in semiconductor devices. And so in a diode we have to include a low doping concentration, high resistivity region in order to achieve a specified breakdown voltage. Here's a diagram that's then a more accurate description of a diode, where we have the P region on the left and the N region on the right and a lightly doped region in the center. Here it's denoted N-, which means low concentration of doping. Often this is also called I for intrinsic, and this is called a PIN diode. So we have this low doping concentration in the middle of the diode, and under reverse bias constant conditions, the depletion region extends far out into this N- region with electric fields that are high in strength, that the light or low doping concentration material can withstand. And we get our voltage breakdown from that. Now, the worry is that by having such a large region that is high resistivity, this will increase the on resistance or forward voltage drop of the device. In a minority carrier device though, such as the PN diode, that doesn't happen. And instead what happens to the phenomena known as conductivity modulation. Basically, the holes from the P region can diffuse into the lightly doped region, where they become minority carriers, and they actually reduce the effective resistivity of the material. They provide charges that are able to conduct the current even though the doping concentration is low. And in fact, electrons from the N region can diffuse into this N- region as well. And so we get a large concentration of minority carriers in the lightly doped region that gives us a low on resistance. So it's good that we can get a high voltage breakdown with a low on resistance at the same time. But the bad news is we have a lot more stored minority charge in the N- region, and therefore the switching time is longer because it takes longer to remove all of that charge to turn the device off. So then here are what waveforms we actually observe in a real power diode. So we start out the diode in the off state, blocking negative voltage and conducting zero current with this large depletion region that is blocking the voltage. We then try to turn on the diode so that any circuit that is connected and the diode will apply positive current to the diode and raise the voltage across the diode. Initially, this positive current charges the capacitance of the depletion region and raises the voltage at some rate. Eventually, the voltage of the diode is positive and the diode turns on and starts to conduct current. We may or may not observe some voltage overshoot as shown here. What's happening here is that if we turn the diode on quickly, it's possible that we initially observe the voltage of the lightly doped region without conductivity modulation. So we have a high on resistance, then we have a large forward voltage drop, that might be 10 or 20 volts, but then after a short period we get minority charge and conductivity modulation that brings the forward voltage drop back down to something like 7/10 or 1 volt, and then the diode after that conducts with a low on resistance. When it's time to turn off the diode, the external circuit attempts to reverse polarity or reverse the current through the diode, and we get a reverse recovery transient with current flowing backwards through the diode to extract the minority charge. And the only difference here now is we have a lot more minority charge from the conductivity modulation of the lightly doped region. So we observe that the reverse recovery, which involves removing the recovered charge, and also while the voltage is changing, we're also charging the capacitance of the depletion region. So this reverse recovery can induce substantial power loss in the MOSFET and during the last part of the reverse recovery in the diode as well. But at a minimum we see this large reverse recovery current causing a spike at the MOSFET while the MOSFET is held on with high voltage across it. And so we get large instantaneous power loss induced in the MOSFET by the diode reverse recovery. Okay, so some terminology. So here are the different diodes according to their application. A standard recovery diode typically is one that is intended for low voltage or low frequency applications such as 60 cycles, 60 Hz or 50 cycles, rectifiers. Often these diodes, the reverse recovery time is not specified, but they won't work definitely in a 100 kHz converter because the reverse recovery time is too slow. Fast recovery and ultra fast recovery, or more recently called super or hyper fast recovery, these refer to diodes where the reverse recovery time is specified and they are intended for switching converter applications. So these will have reverse recovery times for fast recovery diodes that might be between 100 nanosecond and a microsecond, or ultra fast might be 100 nanoseconds or below. And nowadays we can get 600 volt PN junction rectifiers with recovery times as low as 25 or 35 nanoseconds. A Schottky diode, we have to mention this. A Schottky diode has a metal semiconductor junction instead of a PN junction. It is inherently a majority carrier device, does not work on minority carriers. As a result, the Schottky diode for silicon rectifiers doesn't have conductivity modulation, nor does it have long reverse recovery times. So that's kinda good, but bad also. Schottky diodes are limited for silicon devices due to low voltage applications. Generally 100 volts and below. They're very good at say 45 volts and below. They switch very fast, although they do have significant junction capacitance that can affect the circuit and cause some switching losses. Recently we have Schottky diodes built with wide band gaps, semiconductors such as silicon carbide or even more recently gallium nitride. These wide band gap devices can attain high breakdown voltages of 600 or 1200 volts in a Schottky diode and still have the majority carrier device. They have larger forward drops, maybe 1.5 or 2 volts instead of less than 1 volt. However, they're very fast switching, and very often in a power converter you will find that if you add if you replace your PN junction with a Schottky key barrier silicon carbide diode. Even though the conduction loss is higher, the switching loss is much lower and overall the efficiency is reduced. So these have found, there are commercial devices that have found some good industry acceptance. The major problem today with them is that they have a very high cost. A silicon carbide 600 volt diode might cost 5 or 10 times as much as a normal silicon diode, but they are definitely they have definitely some measurable reduction in switching loss. Okay, next is the paralleling diodes. With this minority carrier p-n junction diodes, classically we're not supposed to parallel diodes. So for example, suppose we needed a 10 amp diode, but all we have available with us are 5 amperes. So we might say we'll just use two 5 amp diodes and put them in parallel. And in the process, we're hoping that the 10 amps will divide equally between the two diodes, so we get 5 amps through each diode. Generally, this doesn't work. And the reason for this is the temperature dependence of the equilibrium ID characteristic of the diode. Basically, when a diode gets hotter, its voltage goes down for the same current. And conversely, for the same voltage, the current would go up. And this in a minority carrier, say p-n junction diode. So here's what happens. If you put the two diodes in parallel, we apply 10 amps. There's some small difference between the diodes which makes one of the diodes take a little more current than the other, and it gets a little hotter. And so say that this diode on our left, this is diode 1, runs a little hotter than diode 2. That makes it take more current. So instead of 5 amps, it might take 6 amps. And then diode 2 will take in 4 amps. That makes the first diode get hotter yet, the second diode gets cooler, and even more current will go through the first diode and less will go through the second. And so we have thermal instability, wherein one diode hogs all the current. And what will happen is that diode will hog the current, will overheat, and will in fact exceed its rating. And so it will of course it will fail. And once it fails, then that makes all 10 amps go through diode 2, and diode 2 will surely fail as well. So in general, with minority carrier devices, we aren't able to connect them in parallel. With majority carrier devices, the forward drop goes up as the temperature goes up, and it may be possible to parallel these devices. So if you want to get minority carrier diodes to share current, we have to do what we would consider countermeasures, so we can prevent breakdowns of these devices. We can sort devices and select match devices. We can package them on a common thermal substrate so they run at the same temperature. And if you want to build a high current module of diodes, that's exactly what's done. Or we can try to build some external circuit that forces the currents to balance between these two diodes. Usually that circuit takes up a lot of work to make to work, and generally what we would rather do is find a large enough diode and just use one. And lastly, we've discussed the diode reverse recovery. It actually induces some switching loss in the MOSFET in let's say a buck converter. Sometimes we have circuits where the diodes is not directly connected to a transistor. And here's an example of one. This often happens in transformer isolated converters, or in some other converter circuits that have effectively an inductor that provides current to the diode. So in this example, let's model the rest of the circuit with some switched voltage source that is shown here. It's initially a positive voltage, and at some time it switches to a negative voltage. And what's shown here is an inductor, and then a diode with its junction capacitance. Here, as seen, is shown explicitly. This is the capacitance of the depletion region. So initially we have positive voltage applied. That positive voltage makes positive current flow through the inductor, and that current flows through the dial, turning the diode on. So the diode is on, and basically this positive input voltage V1 appears across the inductor, and the inductor current increases with the slope given by the voltage divided by the inductance, and rises to some positive current. And at this times where we switch the input, the voltage is negative. At this point, we had a negative voltage applied across the inductor. The inductor current is still positive initially, so this positive current continues to flow through the diode, which keeps it on. And so the input voltage appears across the inductor, and the inductor current then ramps down from the negative applied voltage like this. Eventually it reaches 0, and there's an interesting thing that happens. Well, just because the inductor current is 0 doesn't mean the diode turns off. We have to first remove its stored charge, and that takes some time. So during the reverse recovery time of the diode stays on. It maintains its same forward voltage drop, and so we have the same negative voltage across the inductor, which continues to charge the inductor current negative. So we get some negative current in the inductor, and then at some point right here, finally the diode turns off because its stored charge has been removed by the negative current, and at that point the diode switches off. And what happens in the inductor current? We built up some negative current in the inductor. We're storing energy in the inductor, 1/2 Li squared, and the inductor current has to go somewhere. Well, the only place it can go is through the capacitance now. So the junction capacitance of the reverse bias diode will form a resonance circuit in connection with the inductor. That resonance circuit has some initial condition and current, and so we get the inductor and capacitor forming a resonance circuit that rings like this. And we get a diode voltage that rings as well. Eventually that ringing decays to 0 by parasitic losses in the circuit. So we have the resistance of the inductor winding, we have core loss and other such losses in a circuit, and something damps out the ringing and makes it decay to 0. Whatever that is, whatever damps it, it dissipates the power, and so it will get hot. And this is in fact a form of switching loss. The diode induces energy storage in the inductor, which is then lost after the diode turns off. However much energy loss that is, let's call it W off right now. It is the energy lost and the diode turned off, transition, and then lost. That energy multiplied by the switching frequency is another form of switching loss. And so in our power converters, when we see ringing like this, that decays, that ringing is an additional component of switching loss. And in this particular case, we can actually calculate how much energy there is. The recovered charge, which is the area under the curve, is defined as the integral of the current during this time, as usual. So then the recovered charge is something that is a property of the diode. You can also calculate the energy stored in the inductor during this interval. And basically, if we integrate the voltage on the inductor, its negative voltage, times the inductor current, That's the integral of the power, which is the total energy stored in the inductor from here to here. Well, the voltage is minus V2, and the current is the current waveform, but we can plug V2 into here, and since V2 is a constant, the integral of the power is actually just the constant V2 times the integral of the current, and the integral of the current is the recovered charge at the diode. So what we get is that during the diode reverse recovery, timed energy is stored in the inductor equal to the applied voltage V2 times the diode stored charge or recovered charge. That energy becomes stored in the inductor, so it's equal to 1/2 Li squared at this point right here at the peak of the negative current, and that energy rings between the inductor and the capacitor during these oscillations and eventually gets dissipated by whatever damps the ringing. So this is the amount of energy we'll lose every time this diode switches off. We multiply it by the switching frequency to get the switching loss. And so the diode can induce switching loss, and this reverse recovery will induce ringing. That is another form of switching loss.